Isotropy of Euclidean space. In Newtonian mechanics, the space is assumed to be a Euclidean space. You learned Euclidean space for a very long time from elementary school. You learned number line that has a one-to-one correspondence with the real numbers, and that real number is assumed to be in correspondence with the actual Euclidean space, and we believe that physical space is identical to the ideal mathematical model for the physical one-dimensional space is assumed to be the Euclidean space. When you learn special theory of relativity, this belief will be broken down because the space is not Euclidean anymore, and it is actually the Minkowski space, the mixture of the space and time. But for the time being, as far as we consider a motion that is very slow in comparison with the speed of light, then the space, our assumption that the space is Euclidean is correct. We study the consequence of isotropy and homogeneousness of the Euclidean space in this problem. A point charge is at the origin. A point charge is at the origin of an isotropic electric field at the origin, and the isotropic electric field and the point mass is the origin of the this was the point charge produces the electric field that is isotropic. Point mass is relevant to the origin of the isotropic gravitational field. Based on this, explain why it is natural to postulate that Euclidean space is isotropic. The point charge has a rotational symmetry of about any axis of rotation by any angle. If you rotate this point in any along any direction and about any angle, point is point. The same is true for a sphere. A sphere has rotational symmetry. If you choose an axis passing through the center of the sphere, and if you rotate this sphere by any angle, it is still the same sphere. So this is called the rotational symmetry. If the system has a rotational symmetry, then the produced electric field, for example, it is a uniformly charged sphere, then the electric field produced by this is symmetric. This is the consequence of the fact that space is isotropic. If it is not the case, even though the charge distribution is uniform, some electric field is very strong along some direction, and the other direction, the electric field is weak. That is not true in nature. That means, the space seems to be isotropic. Isotropic means it is equivalent. Every direction is equivalent. So the produced electric field due to a point charge in space is isotropic. That is the consequence of the isotropy of the Euclidean space that we are working on. The electric field is defined by the electrostatic force divided by the charge. Usually delta Q is assumed to be very small. Actually, the electrostatic force is between two charged particles, and this fixed one is called test charge, and the other that generates the electric field is called a distribution of charge in general. In that case, the electrostatic force between this distribution and a point charge, the electric field is the force divided by the test charge. This one is assumed to be delta. And the reason why we take this delta Q, the limit delta Q goes to 0, means we do not want to modify the electric field generated by the charge distribution. And this is a mathematical approach that delta Q goes to 0. In nature, there is no such kind of limit because the smallest charge in nature is the electric charge. Even though it is very, very tiny, it is a finite number. So it is just our convenience, even though it is not realistic. Anyway, once you compute the electric field, our computation for the other charged particle with a different charge is very simple because we multiply the electric field by the test charge Q, then we can always obtain the electrostatic force due to the charge distribution on any point charge Q. So electric field is the electrostatic force divided by the charge of the test charge. What happens if we consider point charge? Point charge instead of a complicated charge distribution, and source of the electric field is a point charge Q. In that case, because of the isotropy of the Euclidean space, the electric field will be radiated all over the space. The strength of the electric field is proportional to the charge Q is reciprocal to the square of the distance. So we call it is satisfying the inverse scale law. So R, according to Pythagorean theorem, R is the sum of the squares of the Cartesian coordinates and take the square root. This is ER hat. This is the unit radial vector, radial direction, and unit length. So unit radial vector that can always expressed as a position vector divided by its magnitude. So it is 1 over r squared. This one has the magnitude 1 and dimensionless. However, if you revive the numerator x in this way, the power in the denominator becomes 3. So we have a square root. This one is a radius. So this is the electric field generated by a point charge, and that is a symmetric on the rotation. And this is also true for the charge mass distribution. So both the electrostatic force and the gravitational force satisfy the inverse scale law. There is some difference. The overall coefficient, 1 over 4 pi epsilon 0 square, epsilon 0, is replaced with minus g. The reason is that minus g means the electrostatic, the gravitational acceleration is along the direction to make them attractive. So gravitational force is attractive only. Here, there is a missing factor. There is a product of the two charges that is relevant for the force. And if we kill the test charge, then only the source charge will appear in the numerator. And depending on the product, sign of the product of the two charges, we determine whether the force, the electrostatic force, is attractive or repulsive. Only if the signs of the charges are opposite, it is attractive. If they are the same, it is repulsive. Next, we consider the charge distribution. For simplicity, we consider uniformly charged circle. Uniform means depending on the length, delta L, we have some charge. It is called lambda, and this lambda is called charge density per unit length. So sometimes it's a linear charge density. If a charge is distributed over a surface, then we would rather define the charge density per unit area. So this is area charge, also called areal charge density. So according to Coulomb's law, the electric field is produced by a point charge. The coefficient is this, and source charge is there, and the distance between the source and field point. Here we have chosen a field point. Field, it is not mathematical field. I told you the field is a function of a position. Sometimes a function of both position and time is called field. Physical field, electromagnetic field, gravitational field, they are all function of position and time. So field point is usually written as P, and source point is usually written as Q. And displacement from the source to the field is very, very important in our computation. This one is usually written as a prime, and the field point is this. So this is the contribution of the tiny charge dq, and according to our assumption, it is proportional to the length, and the proportional constant is lambda. That is what? That is the density. So density multiplied by the length of a very infinitesimal wire. Because it is on a circle, radius times angle will be the arc length. So it will be replaced, this dq will be replaced with this lambda r d theta. And we want to find the theta or r dependence in the denominator. And actually, r is the radius of a circle that is a constant. So the only variable in this problem is angle theta. So what we want to do next step is express the denominator as a function of r and theta, and we will integrate over the whole angle. So in here, electric field is the sum of the tiny pieces, and each tiny piece satisfies the Coulomb's law. Sorry about that. We have electric field, it should be cube, and the numerator should be x minus x prime. Okay. So this is what we just have done. And what's that? Lambda is q over circumference of a sphere, this 2 pi r. Substitute this, and we find net charge q d theta over 2 pi. So this one, this dq has been obtained, expressed in terms of angle theta and charge q. And what about the vector, this unit radial vector, and this capital R starts from the source and it ends up with at the field point x. And in our problem, x is very simple. Our field point is at the origin, so we substitute the 0 vector. So x prime is parameterized in this manner, cosine and sine, and we have radius. We substitute this expression in here, and x is replaced with 0. Therefore, this is the final form for the integrand. Substituting this one into integrand, we find this cosine and sine function integrated over the whole period. So without knowing the integral table, we know it is a vanished, both of them vanished independent. And sure, I can make use of the integral table using the fact that sine theta's differential is cosine theta d theta, and cosine's differential is minus sine theta d theta, and we integrate over the whole circle, therefore it always vanishes. So this one shows that the electric field vanishes after integration. But even before we do the integral, we know that there are two symmetric contributions on the opposite side. And the electric field element generated by this point Q with the same angle d theta and the other charge Q prime, their magnitude of the contributions are the same. However, they are opposite direction. This direction is this direction. We assume that Q is positive. If Q is negative opposite, anyway, they are of equal magnitude at opposite direction. So even before carrying out the integral, we know they cancel from the small element exactly. So we don't have to compute this. And this is a center of symmetry. We don't have to calculate this. So the electric field at the center of a uniformly charged circle is actually 0.